All right, so here we are. This is the Hacking Mobile Devices class, and all I want to do is start talking about iOS apps, continue talking about them. We're going to do the first chapter here. I'm not going to demonstrate a project tonight because I still haven't finished rewriting the projects to handle these apps that come in 4 pieces. I know how to do it, but hopefully over the break, we're getting a week off for spring break, I should be able to rewrite the last 2 projects which require you to use password managers on the phone, and I really want to have an archived version of the password manager, so you'll all be using the same version, instead of using the current one in the App Store, which will change and not have the right flags and such. So let's take a look at the analyzing iOS apps. Almost all the class has been about Android, but now we're going to talk about iOS. We don't have any hands-on iOS projects because it's too difficult to distribute phones to all the students, which is what we'd have to do. I've tried to do it in the past and it hasn't worked out very well. But you'll find that it's very much like Android. So we'll talk about the security model, the apps, and jailbreaking, and there are some topics for the next class too, which will be in 2 weeks. There's no class next week, it's spring break. So the security model for iOS, it has a secure boot chain which is really strong. It is really very careful to only boot authentic Apple operating systems and to make sure that the boot process has no step has been compromised. This is like Microsoft Secure Boot that you can get on Windows machines now, but it's very strong. It's so strong that I think there never has been an iOS rootkit. There's been no rootkit you can put on an iPhone ever. There are attacks and there are flaws, but I've never heard of a rootkit, which is something that lives right in the heart of the operating system and changes its functionality, because the boot chain is there to prevent that. And Microsoft tried to add the boot chain to Windows. When they had Windows 8 on ARM, you would get a tablet, and that would have a similar secured boot up feature. It wasn't a success in the marketplace, but that was the idea. So you have code signing. Your code is signed with a digital certificate, so it can't be modified. You detect when it's modified. Your processes are sandboxed. Remember, in Android, every app runs with a different user account for their sandbox. iOS has a different technique of doing the same thing to make sure that each process has its own memory and it doesn't and storage, and it doesn't mix with other apps. It encrypts the data at rest. This is where iOS was very ahead of Android. Ever since the iPhone 3S, everything you put on an iPhone has been encrypted with AES. And this makes it possible to sell your phone, because you can reset the phone to factory defaults, and all that does is delete the key. All the data is now lost irretrievably, and you can safely sell the phone and nobody can get your data. There are Android phones that can do this, but there are also Android phones that cannot do this, because Android is a very diverse marketplace, and some of them don't enable the more important security features. We'll talk about exploit mitigations for apps written in native language, which is basically C or C# or something like that, things that are compiled down to machine language like Windows apps, and therefore have the vulnerabilities of memory corruption like Windows apps. And here they are: address-based layout randomization, non-executable memory, and stack smashing protection. These are the main defenses to prevent exploitation of native code. And the same thing's true of Windows native code. The main thing you're trying to prevent here is buffer overruns. Let me check for comments in the Twitch. All right, there are none. So here's what you have. Here's the steps of booting up your iPhone. It has several steps, and each step is cryptographically signed and verified. So if at any step it fails, it will not boot up. So first you start with the boot ROM. This is the read-only portion of the microprocessor, and this contains the public key for Apple's certificate authority, so it can it can verify the next step, making sure this is really signed based on that public key. So this boots up the phone, and then it goes to the next stage of starting up, which is the low-level bootloader. This will first be verified. Boot ROM will verify the signature before it lets this run. This will then find the iBoot image in flash memory, and then verify its signature and make sure that it's okay. If it's not okay, it will fall back to a recovery mode, some kind of emergency recovery mode where you can try to repair the phone. Same thing's true of many other devices like Cisco routers and Android phones for that matter. They have an emergency recovery mode you can use to reinstall the operating system if it gets corrupted. So if it does pass the test and decides this is a good iBoot, it runs the iBoot, and that will verify the iOS kernel and go there. That will load the user mode environment and the OS So, you start your phone, it shows you an Apple logo, it shows you a little progress bar along the bottom, all this stuff is going on. And when it finally gets the iOS kernel going, then you'll see your phone face with your apps on it and your login screen and such. So all iPhones since the 5S have got a secure enclave, which is a cryptographic coprocessor. This is like the trusted platform module on Windows machines. And the point of this is the cryptographic keys are not stored on the flash drive, and they are not stored anywhere in the memory. They're in a special chip, which is not anywhere in the address space of the processor. And this means even if you get infected with malware that gets root permissions and can access the entire memory, it still can't steal the key because the key is stored in a separate cryptographic module. That's the point here. So it's key management for the data protection API and the fingerprint data. So that's the secure enclave. This is ARM Trust Zone. It's not, I think, a separate chip. I think it's just part of a processor chip. I think that's what the ARM Trust Zone is, but I'm not really quite sure how they implement it in hardware. And therefore, the point is, even if the device is jailbroken and the attacker can run code with root level permissions, they still can't steal the secrets because they're in a separate place. They're not anywhere in the address space of the processor. Now, there have been some attempts to bypass this. There was an attack where you could deduce some information about it by looking at cache memory, and this is a whole series of such attacks based on caching. In Windows environments, it was, on desktop machines, it was Spectre and Meltdown, and there's a new one that just came out for the M1, M2, and M3 Macs. There are ways when caches that are there to speed up processing sometimes leak secrets because the secret goes in the cache and you can tell something about the secret for that way. So there have been occasional small attacks that leak things out there, but nothing significant, I think, has ever penetrated the secure enclave on an iPhone. All right. So then there's code signing. Now this is actually very obvious on Macs. When I first started using a Mac, I was sometimes really bothered because I would launch something like a browser, and sometimes it would take like 30 seconds to launch, and sometimes it would launch right away. And I checked in Wireshark, every single time you launch an application on a Mac, it sends data to Apple, and only launches if it gets approval from Apple. And sometimes Apple is busy because they're putting out a new update and their servers are slow. So it validates signatures remotely every time you execute. And the same thing's true with Windows since Windows 10. Every time you go to a website, they send it to Microsoft Cloud Services to see if it's malicious before you can go there. So people got real upset at first about the privacy intrusion of this, and then everybody got used to it. Anyway, so there's a similar thing on your phone. Your apps have to be signed, and only code signed with a trusted signature can run. Notice this is very different than Android. In Android, you can use a self-signed certificate to sign your app. So it doesn't get verified anywhere, so anybody can distribute an Android app and it'll run on any Android phone. But on Apple, you can only distribute apps through the App Store, and they have to be signed by Apple. You have to get Apple's approval to sell your app. With a few exceptions, you can have a provisioning profile where you install a provisioning profile, so now you can put in apps that did not come from the App Store. But you have to install a profile saying you're going to accept these alternative signatures. So the App Store is the main thing that makes iPhones more secure than Android. This limitation that you can't just get an arbitrary app from any website, you can only get an app from the App Store, means that there is almost no malware available to put on your phone because Apple is pretty good at cleaning out the App Store. Not because they're technically very good at scanning, but because they require you to identify yourself with a real credit card so they know who you are. And if you put malware in the App Store, they will ban you and you'll never be able to sell another app. And people make a lot of money by selling iOS apps. Android users expect every app to be free, but iOS users are used to paying money for the apps. So you can make a real living selling iOS apps, and you don't want to get kicked out of the App Store for putting malware in there, so almost nobody ever does it. It happens sometimes, but it's very rare. So you can basically use an iPhone without worrying about malware at all, for all practical purposes, unless you are such a target that somebody's going to spend $1 million and get Predator. I think that's the stuff. There's a fairly expensive spyware you can get from basically military weapon sellers to infect phones, but it's not something normal users have to worry about. And the App Store doesn't let you do anything fishy. You can't get a firewall or an antivirus from the App Store or much in the way of a hacking tool or anything. They won't let you use private APIs. They won't let you download and install further executable code because they don't want any code to go in that doesn't get approved through the App Store. So they try to make sure that they control all the code in all the apps, and they make sure it always obeys their policies. All right. So the sandboxing. They do not use a separate user account for each app. Instead, they all run as the same mobile system user, but they're contained in their unique directory, and there is a kernel extension called the XNew Sandbox, which separates the apps. And I don't know exactly how it works. I know it's gone through many versions. It started out as Seatbelt, then it was updated to the App Sandbox, and now it's even stronger in iOS, considered to be very strong. So then, of course, you have permissions. Your app will be asked for permissions to use your camera, your microphone, your address book, to read your saved media and such, your photographs and all that jazz. So it has to ask you for permission just like Android apps. And as I mentioned before, the entire file system is encrypted with AES. Before you ever use your phone at all, makes an encryption key, so all your data is encrypted right from the start. This is what you must do if you want to have security, because SSDs have automatic repair. If a block of data on an SSD goes bad, it will silently replace it with another block and continue working, and the old damaged block can never be accessed and can never be erased, and it has some data in it. So if you were to use a phone for a while and then turn on encryption later, you don't know that some of your personal data hasn't moved into an area that you can't erase anymore. So the only way to make it secure is to turn on encryption before you ever start using it. So everything you ever put on the phone is encrypted, and then even if it ends up copied into a bad block or something and not erased, it doesn't matter because you're going to delete the key, and there'll be no way anybody can break in. So it works very well. The device decrypts the file system on boot up. It's only encrypted at rest, and if you remote wipe or reset to factory default, it just erases the key, and then you can know that all that data is very secure. And real forensic companies have tried this. A forensic company bought 100 used iPhones from eBay and tried to get data off them, and they couldn't get any data off any of them. This really works. So the data protection API, you can also encrypt individual files and keychain items with a key derived from your passcode, and then these items become inaccessible when the device is locked. All right, and so then there's the standard exploit mitigations. Let me check for comments. All right, there are none. These are the same exploit mitigations you find in Linux and Windows malware. The simplest one is write or execute. When you reserve memory to be used by any app, you choose either to make it writable or executable, but not both. That way, any data that comes in from the user, like a username and password or something, goes into the writable area, but it cannot be misunderstood as code and executed. So this stops a whole bunch of attacks based on the buffer overflow attack, where you'd put in a string and then you'd somehow trick the computer into executing that string as executable code. So this is implemented with ARM's Execute Never feature, XN. That's how they did it. So pages marked as writable cannot later be reverted to executable. So this is also in Windows. It was called Data Execution Prevention, and it's in every other modern operating system too. The only operating system I've come across that doesn't have this feature is the Raspberry Pi 3, which amazingly doesn't have it. But and probably small Internet of Things devices, like your smart light bulbs and smart thermostats, might not have it. But all modern operating systems have this defense. Then return-oriented programming is how you bypass this. You might think nobody can hack into your device if they can't write and they can't execute anything they write in. But what you do is you write in a bunch of addresses which point to code that was already there. So instead of injecting code and running the code you inject, you use the code that's already there, like in an operating system module, and you just build your exploit out of that code. This is called return-oriented programming. You just have a series of addresses that you write into the writable area, and then you execute code at those addresses. So those addresses are used as data to point to addresses of code that the developer put there. So you don't add any code, you just reuse the commands that the developers put there, but you use them out of order so they have unexpected results. This is called return-oriented programming, and we'll do it in the exploit development class. One way to protect against that is address-based layout randomization. The idea being every time you launch a process, it randomly relocates in memory so you can't find the address. And that's the idea. This makes it more difficult to build those return-oriented programming chains. It has weaknesses, and in every operating system I've ever seen, the main weakness is it doesn't apply to all code. Some code does not randomize, so you can use that code. Anyway, another thing is sometimes there are memory disclosure bugs that leak out addresses so you can find out where the code is running, and so on. Anyway, this feature is called position-independent execution. If you compile your code with this feature, then it's ready to be relocated in memory. If you compile it without this feature, it cannot be relocated because it compiles into machine code that has hard-coded addresses that have to be in that specific place. All right. Another one is stack smashing. The stack is the temporary area where you store variables used in a routine, and you store variables like string variables, and then at the end you have the return pointer, which is to return to the function that called you. So if you can overrun the limits of string storage, you can change the return pointer and go to a different address. So instead of the program continuing to run the code the developer put there, it now runs some other code the developer did not intend to run. And that's how you take over machines with buffer overflow exploits. And the solution here is to put a random value at the end of the stack before the return pointer, and then verify when you return that that value has not changed. And if it has changed, that means somebody performed this overflow and they wrote in areas of memory that we're not supposed to be writing in, and your app will just terminate and say this is a stack smashing detected. This is a common defense. That's a stack canary. And it's named after a canary in a coal mine that you would put on a stick and move ahead to see if the air was bad in coal mines. So this is the same thing. That little value will tell you if somebody has been overflowing the buffers.
In the latest one, in the latest even ARM, they do not the random number. They use like encrypt some your password or some user identification.
Oh.
To encrypt encrypt the value in there.
Oh, I'm not aware of that one. I know there are various canaries that have been used.
The ARM uses it too.
ARM uses.
Yeah.
Okay, that's interesting. I hadn't heard of encrypting a password or something to make a stack canary, but it's interesting. Okay.
Because it's they were thinking of like a data center.
Yeah.
About a user, so they have to have somewhere identified individual.
Oh.
user.
Oh, that's very interesting. Yes, if multiple users are going to be using the same process. You need to know which one.
You don't want user to pick the other users.
Yeah, that makes sense to separate multiple users. Good, thank you. All right, so the apps. There's three kinds of apps. Native apps, which are compiled to direct machine code, like Windows apps, apps that run in the browser, so they're written in languages like JavaScript, and then hybrid apps. The most common apps on iPhones are native apps. Notice this is very different than Android. In Android, almost all apps run in Java virtual machines. But in iOS, they are native code, just like your Windows apps. They're written in Objective-C or Swift, compiled to native code, and then linked to libraries that do this. All right. And so your browser-based apps are just web pages that load in mobile Safari, and of course they use HTML and JavaScript and so on, and they're basically just web apps. Then you can have hybrid apps that are used to display browser-based apps and somehow mix these two features together. So when you distribute your app, like I say, the normal way is in the store, then you need an Apple developer account. You can run 100 on just 100 devices for testing, but then you have to get approval to distribute it to the wide world, and they have manual automated tests, and there's huge complaints about the App Store. Developers have complained for years that Apple will just rip you off. Like they will approve your app just long enough for them to make a copy of it, and then they'll kick you out for competing with them and things like that. So they're very abusive, and so Europe has finally cracked down on them earlier this month. The European Union has declared that Apple cannot restrict phones to only use the App Store. They said they have been too abusive. Also, they charge 30% of all the money that people spend on apps, which is considered ridiculous and expensive. And so now European phones are going to have alternative stores other than the Apple Store to download apps for, and I haven't seen any reports yet of how well that's going. But they had to begin that process last month because another European internet regulation just kicked in. That doesn't apply to phones in America yet, but probably after it's been in Europe for a while, they'll probably do the same thing here. They've done that with other things. So then you can also have enterprise distribution. You might want to develop your own apps just for your own enterprise users. So what you can do is get an enterprise developer certificate, and then you can run those apps on phones. Apple screens the developers entering the program, though. You can't just be a random person doing it. And so this has happened before. An expired developer certificate was used to make a jailbreak. Jailbreaks are the hacks that escape all these Apple restrictions. They let you load things from non-Apple sources and get into the operating system and change things. This is getting full control of your phone. And Apple doesn't like it, and they block it. So just like the forensic companies find vulnerabilities and use them to get the data off the phone, the jailbreak communities find vulnerabilities and develop jailbreaks to get in the phones. Apps are just called an IPA archive, and just like Android apps, it's just a zip archive containing various things. It's got an app, it's a data compiled code and resources, it's got artwork, it's got metadata, and so on. So this is very much like the Android apps with the manifest and so on in it. Before iOS 6, every app had access to everything on the phone. So that's, of course, not a good idea. Now, in iOS 6, they introduced these categories like microphone, Bluetooth, social media, calendar, contacts, just like on Android. And now when you install an app, it will say, this thing wants to access your contacts, is that okay? Just like Android does. And then you'll have a list in your settings where you can see which apps are allowed to access my contacts, just like you can in Android. All right, and then there's location information. You can say app never gets information. It's only while it's in the use or always has access. I see this all the time. These are the kind of settings of levels of permissions for things. And so I mentioned jailbreaking. Jailbreaking is, the main reason people jailbreak is to get pirate apps. You can get pirate copies of games. You can get unapproved apps. One of the early reasons this happened when the iPhone was new is because people wanted to use their iPhone to reach the internet through the cellular network, and that was not approved, so they made a unapproved app on the Cydia App Store to do that. If you jailbreak your phone, you could then run this forbidden activity on your phone. So this, of course, weakens the security of the operating system. It's now allowing unsigned code to run, and therefore most iOS malware runs on jailbroken phones. And one common flaw is people jailbreak their phone now opens an SSH server, and there is a known default name and password, and they don't change the password. So you can totally just hack in by using the default password of Alpine, and that's how most of the early iOS malware worked. iKey was the first phone that would just rickroll you by playing this irritating video. Then there was another one that made phones into bots and phished the data sent in the phones to Dutch users. Then there was Uniflawed Baby Panda from China that would hook functions to steal the Apple ID and password. So, and all these just relied upon your phone being jailbroken and I think having the default name and password there, which is why that's the thing. When you jailbreak your phone or when you put a custom ROM on your Android phone, you must understand that you have now taken on responsibility for the security of your phone. And if you don't know what you're doing, you're likely to open a security hole. So here's the kinds of jailbreaks there are. Untethered jailbreaks are the most valuable. You're able to modify the phone, and the phone will now permanently stay jailbroken as you carry it around and reboot it and install apps and all that. A tethered jailbreak requires you to be connected to a computer to start the phone. Otherwise, you end up in recovery mode. So this is possibly of some interest to like a researcher, but it's not practical for an ordinary user who just wants to carry their phone around and use it with the pirate apps on it. And semi-tethered will let you start into a jailbroken state, and then you can use your phone and carry it around until you have to reboot it, and then you have to connect to your computer. So those are the types of jailbreaks. Jailbreak Me version 3 was a really great one. I remember I used this one. It was awesome. You could just go to a website, and it would just have a PDF file which exploited the PDF reader on the phone, and blam, you were jailbroken. I did this for a friend of mine. So it was very easy. This used a integer signedness issue to get code execution of return-oriented programming payload. And so that was fine, but that was on really old iPhones. Then the evasion jailbreak came later, used bypasses and logic bugs to get in. And now, of course, we got the checkmate vulnerability, one I mentioned before. Check Rain jailbreak is the newest one, that works on phones up through, I think, iPhone 11, and can't be patched. It's in the hardware. So, all right. So after you jailbreak it, you then install OpenSSH in Cydia. Now you can connect via Wi-Fi or USB. The default credentials are mobile Alpine for the low privilege user and root Alpine for the root user. And so now you have root access to your phone. And the end result is very much like what we've done with Android, where you can make a rooted Android phone, and then you can mess with the operating system and collect the data and so on. Just checking for comments. There are none. All right. So Cydia is the app store for the pirate apps that you put on, not necessarily pirate, but most of them are, the apps you put on jailbroken iPhones. Then there's the thing called Big Boss Recommended Tools that gives you a whole lot of useful command line Unix tools. Apple has some tools you use to manipulate apps. The apps are called Mach-O binaries. Windows apps are called portable executable apps. Linux apps are called ELF-ACKS, executable link format, and Apple apps are called Mach-O. That's the format they're in. And so they run on OS X or Linux. So OTool will show you the object file, and this will reveal the libraries and symbols and method names. You can see basic structure about what libraries the app is using.
You have to jailbreak the phone to install these tools, right?
You put them on a Mac typically, not on the phone. I think in principle you might be able to run them on a phone. Normally you'll run them on a Mac. And then you use them, you suck apps down from the phone with either iTunes or with SSH, and then you analyze them here and take them apart. I had some projects where we did this, but it turned out to be really hard to do because you could only do it on a Mac, and you couldn't really do it with the phone unless you had exactly the right version, and it was really hard to make it possible for very many students to do it.
So we try to go to the Bluetooth interface?
No, not Bluetooth. Typically USB. Just like the Android, yeah.
So it's easier to set up the USB on the phone to...
You have to jailbreak it first, and then you can turn on something like USB debugging when you install SSH.
So that means you have to jailbreak the phone in order to use all these tools?
Yes. Well, now you can use these tools on apps from the App Store without a phone, but you have to download them from sort of pirate site, because normally the App Store will only install onto a phone. So, but you can get an app and manipulate it. We have these APK files from Android that we were using. You can do that with iPhone apps too. Anyway, so OTool lets you see the basic structure inside the app. NM shows you the symbol table, and LiPo is a common one. If your apps, this is what I was saying about the project I haven't done yet. Last two projects use password managers on Android, and they are compiled from multiple architectures. There's i386, x86, 64, and perhaps ARM all in the same app. So there are many pieces. And the same thing's true of many iPhone apps. They have a 32-bit and a 64-bit version. And so LiPo is what you can reveal the various versions of the app that are in there, and you can remove them. You can simplify your app. GDB is the debugger you use for Linux tools. It turns out Cydia's version isn't much good, but Radare's version of GDB is better. And there's a code signing tool, of course, to display or add signatures to the app. And there's Sorix Code Signer, which is the code signer used for Cydia apps, not Apple official apps. Sorix is the name used by the person who made the Cydia, the repository for the App Store for jailbroken phones. Now, in principle, you can install an app from anywhere on a jailbroken phone, but in practice, what most people do is they just use the open source App Store, the Cydia, that's there. All right, and normal app installation uses the install D service. IPA installer can install unsigned apps on jailbroken devices. So, the Sorix did a lot of work making tools to make it possible to put apps on jailbroken phones. And there's a very vigorous Apple jailbreaking community that is constantly hacking into app phones and analyzing all the Apple devices and finding weaknesses in their security.
But all these tools use unofficial apps.
Unofficial apps, yes.
But how good are those unofficial apps compared to official ones?
Well, it's a good question. As far as I've heard, most of the apps on the Cydia store are perfectly fine to use. In fact, many of them are pirated apps, like games. that were just they stolen from phones.
How do the user know that, there are no funny stuff in there?
That is a good question, and I don't know. Absolutely, those apps might have malware in them, and I'm not aware of any real effort to clean it or anything. I think it's all just reputation. So it's like Android, you're just taking a chance. Yeah, so jailbreaking your phone is basically moving from the iPhone environment really over to the Android environment. But a lot of people do it because they want to get these pirate apps. But of course, it's more dangerous. For all you know, there's malware in there. Absolutely. All right, so your jailbroken device gives you full access to the file system. Now, if you're not jailbroken, you can only reach certain areas. You can pair to a computer over USB, even if you're not jailbroken, and there are certain apps that will let you explore parts of the file system, but you're only getting like the data from the apps. You're not getting into the system files. And that's like you can make a backup with iTunes, although I think they might have a different app now, but you're only getting the data from the apps. You're not getting a copy of the operating system. So on a jailbroken device, you can go in and see the same stuff you'd expect from any Unix system. There's an applications folder, a var folder, a private var folder for where voicemails go, SMS data here, photos, videos, and contacts here. These are locations you'll find on a jailbroken device. There are plist files, which are binary configuration files for the apps, and plutil is the tool. The same thing's true of apps on OS X, on a desktop machine. The plist files are essentially what replaces Microsoft's registry. It's where all the settings for all the apps are. And then you have cookies. Your web pages have cookies, and you can open them with a binary cookie reader. And data is often stored in SQLite databases, just like it was on Android. All right, so let's try a Kahoot. I have a Kahoot here. It is 2A. There. Looks like this is all we're going to get. Oh, maybe not. All right, I'll wait a few more seconds. All right. All right, so which step will fall into recovery mode if the signature fails? It's the low-level boot. You start with boot ROM, you go to low-level boot, and if it doesn't like the operating system it finds in iBoot, it falls back to recovery. All right, which feature was called seatbelt? That's the sandboxing. All right, which mitigation uses XN? That's non-executable memory, and the Intel version used on Windows machines is called NX, so it's all very similar. Anyway, that's the feature that makes it possible to mark areas of memory non-executable. All right, what mitigation do you bypass with RAM? You bypass non-executable memory. Instead of injecting code, you simply inject addresses, and then you jump to those addresses. So you do not actually execute any of the code in the NX memory. All right, what was the first iPhone worm? iKey, right? And what's the root password on an iPhone? It's Alpine, and therefore if you jailbreak your phone, the first thing you should do is change that password. Stop the recording.